So last Thursday, we finished the lab with the following question. What do we use these EBMs for?
Everywhere.
So what is a practical application where this kind of many-to-many or one-to-many is required?
So we're going to see some examples today in structure prediction. So whenever there is a latent variable, to some extent, you've already used energy-based models in the sense that there is an interpretation of classifiers as actually energy-based models, where you, when you plug the scores coming out of a classifier, right, before you run into the softmax, your scores that go into a classifier, you can interpret those scores as energies or as negative energies, right? If you think of them as if the softmax doesn't have a minus sign in front, then the scores are the weighted sums before you go into the softmax can be interpreted as negative energies. So when you go through the softmax and you minimize the log loss, the log the log of the score that your system gives to the correct answer, right? Which is what we do whenever we do classification very often. The effect of this, because of the softmax, is going to be to push up on the score of the correct answer and push down on the scores of the others because of the normalization factor. Mm-hmm. And so you can see this as a form of contrastive energy-based learning. Okay, it's implicit because the softmax does this for you, but really that's what's happening. There is one score that's being pushed up, or negative energy that's being pushed up, which means that energy is being pushed down, and then everything else is being pushed in the other direction. So it's just an interpretation, right? Now, this interpretation becomes really crucial when you have latent variables, and we'll see some examples, some practical examples today when you have latent variables in things like speech recognition and handwriting and a lot of other applications.
But in the first part of the lab, we saw that we have like one-to-many, right? We have one X, and given the X location, we have the whole ellipse for that location, right? So yeah. What could be like an application of the fact that we have one input, but a continuous set of outputs? Right.
So now this is a topic that has become very, very popular over the last few years, and we'll talk about it probably. We probably won't have time today, but probably next time, on this idea of self-supervised learning. So this idea of contrastive learning that I mentioned last week becomes intractable or complicated or infeasible when the number of alternatives to the correct answer becomes either very large or infinite or combinatorial. Okay, mm-hmm. So imagine that now the correct answer is a sentence because you're doing translation. And what you have to push down on you have to push down the energy of the correct answer and push up on the energy of every possible sentence. Okay, mm-hmm. And you can't do this, right? Because you don't have a way of enumerating. I mean, you do have a way of enumerating all possible sentences, but there's an infinite number. And even if you limit yourself to a finite size, there's an exponentially growing number with the size. So it's basically impossible, right? Okay. So now you have to think, what am I going to do? I can't do softmax over the collection of all things. So I'm going to have to cut corners. And either you cut corners while trying to stick to the probabilistic interpretation of all this, or you say, okay, I'm not going to be able to stick to the probabilistic framework. So I'm just going to say I have a bunch of scores and I need to push down the energies. I'm going to push down on the energy of the correct thing and push up on other things, and crossing my fingers that I'm going to push up on n of things that the energy function will only give low energy to stuff I train it on. Okay. And so because the probabilistic approach becomes intractable when you have a potentially infinite or just combinatorially large number of possible answers, you kind of have to resort to those other interpretation. And the experience, from the last almost 30 years now, 25 years at least, shows that you should get rid of the probabilistic interpretation when you do this, because it leads to over-constrained problems if you really want to stick to it. There's something called a label bias, which I might talk about today.
Okay, I trust you on that.
So, that's a little more about the motivation. Now, the problem becomes even more dire when what you're trying to predict is a continuous variable like an image. Okay. So you want to do video prediction. For example, here's a practical application. You want to build a system that can compress videos very well. Okay. So the best way to compress a video is to look at the past video that has already been transmitted and then try to predict what the next frame is going to be. Okay. You have a smart system that, knows about objects and predicts where, everything is going to be in the next frame. And this prediction, of course, will depend on some latent variable because you can't exactly predict what's going to happen from the previous frames. There are things that will happen that are eminently unpredictable. So you're going to have latent variables that basically parameterize the set of possible things that could happen that you can't predict which one will happen, right?
Yeah, I see.
So now your compression system will just need to transmit the value of those latent variables. Hopefully it's a small number. Compress that and transmit it. And then the decoder at the other end will be able to decode the frame without having, to know all the pixels, essentially, just by being given those latent variables. In a way, conceptually, this is actually how video compression works, except those predictors are built by hand, they're not trained, although there are a lot of startups now that are working on this. And there's projects at Facebook on this as well. Now, the main application, though, of this, of predicting continuous, high-dimensional continuous things, or an energy-based model where the variable to be predicted is a high-dimensional thing like an image. The main application of this is self-supervised learning. So what you want to do is train a system to learn good features without having to resort to labeled samples. Okay, so we talked about joint embedding like last time briefly. I'm going to talk about it again today a little bit, where you have Siamese nets, so two networks that are identical, and you show it two different versions of the same image by distorting one of them or both, and then you train the system to produce the same output for those two images so that it's invariant to those transformations. And then there is another phase, a contrastive phase, where you show two examples that are different, and then you push the two output vectors away from each other. The distance between the output vectors is the energy. And you can think of this as a contrastive method where you want to make the energy for a pair of compatible images low and the energy for a pair of incompatible images large. And the problem, of course, is that you have a potentially infinite number of negative images. Yeah. So now you have to be smart about how you pick those images so that you push things and ends up working. And this is best understood in the context of energy-based model. You can't really sort of have a correct probability formulation of this.
Okay. All right. I think enough motivation for... there is a question here from Alan. So is this similar to interpolation?
Well, I mean, all of machine learning is similar to interpolation if you want, right? When you train a linear regression, right, on scalar values, right, you're training a model, right? You're giving a bunch of pairs X and Y, and you're asking what are the best values of A and B for Y equals AX plus B that minimizes the squared error of the prediction of a line to all of the points, right? That's linear regression. That's interpolation. All of machine learning is interpolation. In fact, much of machine learning. So here is an important point that you're going to get a bigger answer than you asked for, which is that in a high-dimensional space, there is essentially no such thing as interpolation. Everything is extrapolation. So imagine you are in a space of images, right? So you have a color images 256 by 256. That's 200,000 pixels or something. Input values, right? That's 64,000 pixels, but 65,000. So it's 200,000 dimensional input space. Even if you have 1 million samples, you're only covering a tiny portion of the dimensions of that space, right? Those images are in a tiny sliver of surface among the space of all possible combinations of values of pixels. And so what you're doing when you show the system a new image, it's very unlikely that this image is a linear combination of previous images. Okay. Which means what you're doing is extrapolation, not interpolation. Okay. And in high dimension, all of machine learning is extrapolation, which is why it's hard.
Okay, I see.
But this doesn't have much to do with energy-based models.
Are we reading the other question here? How well supervised?
But yeah, I'd rather not answer that question now. We'll talk about self-supervised learning some more. So there'll be like, a whole lecture on this pretty much.
Okay.
Or in fact, I'll talk about this in the first hour today. So maybe you'll get your answer. If you don't, then ask me again.
All right, awesome. Okay, then I disappear and I'll let you teach the class.